the okay, so for this one, please watch the videos on the playlist on the YouTube, and here is the result. So for the Nyquist path, that one is to cover the entire right-hand side of the complex plane. So for this case, we using this, including the entire imaginary axis and bypassing all the possible poles on the imaginary axis, and using the semi-circle with the radius r equals infinity to cover the entire right-hand side. And now for this example here, we locate the locations of the poles, 1 and -1 and zeros, 2. Okay, so by doing this one, follow up the lectures, the videos, we're selecting a few sampling points for our drawing. S1 and S2 is very close to the origin, but above. S3 is below, and S4 is here. And 5 is pretty much here nearby the S4, and this is 6 and 7 here. Okay, so we calculate the value of the GH at S1, at S2, etc., and S7. Okay, so we will be able to label those points, and actually that point, that looking will be like this. So that is GH and imaginary GH. Okay, so here we have calculated those one. So basically those one will be certain complex number. Let me say alpha 1 plus j beta 1, alpha 2 plus j beta 2, etc. Okay. So with those things, we will be able to label it, and S1 will be, so something will be like this. And let me explain. So basically this one is pretty much a circle, okay, and we can prove it. And this is the semicircle, and this one has the radius. This one has the radius epsilon, and epsilon pretty much close to 0. So basically here nearby, if you really want to zoom in, this really is like this. But if we don't zoom in, you can simply using a circle tangent to the origin. That'll be good enough. Okay. And for this one, we can map the point. So for example, S1, and let me define this is the capital S1. Okay, this is a capital S2, etc. So this is capital S1 here. The capital S2 will be to here, and S3 will be here. Okay, and S4, and 5 is nearby S4, and 6 and 7. Okay, and the magnitude here is 2. This one point is S equal to -2. Okay, so that is corresponding, and so I'm going to keep the drawing here because I'm going to use this drawing to explain, to provide a few notes. So that is the drawing of the Nyquist, the plot. So basically that is this one. And again, if we we define the counterclockwise directions as our path. Okay, so now you can see the mapping sequence is S1, 2, 3, 4, 5, 6, 7. This is to follow the direction counterclockwise. So here, from here to here is counterclockwise directions on the path. And we see the mapping on here is S1 and S2, and S3, S4. So basically the mapping onto here is clockwise. So this direction is from here to here. Basically, this is called the conformal mapping in complex algebra. Okay, So from here you can see the direction basically flipped. Okay. So from here I want to make a note. The first one is about the stability of the system. The associated closed loop system. For here again, we've been able to plot the Nyquist, to draw the Nyquist plot onto this system because we have simplified a few steps such that when we draw it, we don't draw an open loop system. But the whole story back to the very, very beginning, we're still concerned about the closed loop system. And how to simplify from there to here, please, again, we have lecture videos there, okay? But here, this system will be something like this. For example, this is our G and this is our controllers. We might have the systems configurations like this, okay? So this is the closed loop. Or we might have this controller is here and this is G open loop. The uncontrolled system, we might have something like this one. Okay, so for the stability of the associated closed loop system will be something like this. So for stability, we asking all the characteristic equations has no root on the right-hand side of the complex plane, so that means D must be equal to 0. Okay, so here for this note I apply is the Nyquist stability theory. Okay, so for that one, the Nyquist stability theory we're saying is n equal to Z minus P. Right. Okay, so now for stability, we're asking Z equal to 0. Okay, so that means n equal to this. So that means for a stable system, a stable closed loop systems, they must have n equal to minus p. If this relation is violated, that means the system won't be stable. The system is unstable. Then we check this. So for this system, you can see this case, how many number of the poles enclosed in this path? 1. So that means p equal to 1. And in this path, we follow is our sign convention. For example, counterclockwise we say we take positive for counterclockwise. So on this case is 1, positive 1. Okay, so now for this case, you can see on the Nyquist, the stability theorem, we converted into this open loop complex plane and saying that what is n? N is the numbers of these corresponding plots encircled the point minus 1, 0, right? Okay, again, here we have a few steps reaching to this point, refer to our lecture videos, okay? So again, what is n? N is the number of the encirclement of this plot on this point, okay? And for this one, you can see really this point is inside this circle, inside this loop, and how many by how many times? One circle, right? But however, this circlement is in clockwise direction. So by our sign convention minus 1. So for this case, this one is n equal to minus 1. So now we check here. For stability, we're asking this must be satisfied. For this example, n equal to minus 1, p equal to 1, so this is satisfied. So for sure, the system is stable. If we want to check, you can check. You can check using the old methods we've been through. For example, you can use the root Hurwitz method, or you can use the root locus method, or simply we directly solve for this one. So the characteristic equation is 1 plus gh equal to 0. So we plug into here 1 plus gh, so that is s squared minus 1 s plus 2 equal to 0. That means s squared plus s plus 1 equal to 0. So for this one, you can check the roots is equal to s1, 2 equal to minus 2, 1 plus 1 minus 4, right? So for this case, you can see the roots are with the negative real part, so definitely this has no roots on the right-hand side. Okay, so using this is a very simple system, so the old method would apply very quickly. But for a little bit more complicated systems, sometimes we know from our experience, sometimes if the system is too complicated, we won't be able to solve the roots by hand, right? So that means for other certain situations, this method would be easier. Be good? Okay, so that is the first note for this. Before I proceed, any questions about the exercise of this? So that should be clear on the videos, right? I tried a lot. So. The second note using this example is you see when we plot this is a portion from S1 to S2, basically is from J. S1 is from J infinity to S2 is J0 plus. And these portions basically sampling corresponding to is this point. This portion I highlight with those dots here. Okay? And then from S3 to S4 onward. So that means S3 equal to J0 minus and 2 to minus J infinity. For this one, that is the point here. You see, these portions are symmetric respect to the horizontal axis. So, which means here for the second note, I want to make it for you is sometimes we don't need to select so many sampling points. Maybe we can only select this portion. The other portion we directly make it symmetric and then flip the plot to there. We can save our calculations. Be good? Okay. So this note is this one. The plot of I would say GH. GH, that means any open loop system. Okay, any open loop systems is symmetric. With respect to, for example, the portions of, let me make a note and say S1 to S2. So that means corresponding is J infinity to J0 and S3 to S4. That means, how to say this one? You know what I mean, okay? So let me just make it. Okay, you know what I mean. So please use your own words. What I mean is simply the plots corresponding to this portion basically symmetric to that one. Okay, so please use your own language and write down something you understand. Okay. The third one is this. Right now we've been taking care of all the drawing on the imaginary axis, and all the sampling points from, in particular, G as 5, G as 6, 7. The 3 points is locating on the parameters with radius equal to infinity. And that corresponding to the plot actually is corresponding to this small semicircle, very close to origins. Okay, and if in terms of the detailed plotting of the Nyquist the functions here, I do require you to show me in detail the rooming at the small scale. I do want to know whether you totally understand how to make it complete in terms of your exercise. However, on the other side, in terms of applying the Nyquist stability theory, which is saying the encirclement about the point here, this point is so far away from here. So in terms of applying the Nyquist stability theory, I don't care about the details. We just make through it. We good? Okay, so that means for applying the Nyquist stability, the plot associated with this one. So let me say S5, S6, S7. So that means on the radius infinity circle. Okay, so you know what I mean. The plot associated with those one can be approximated by 0 plus J0. So basically, the plot is around the origin here. Okay, so that means by taking the summations of the stability, the two things basically here is this. When applying the Nyquist stability theory, you only need to draw a portion. Which portion? This portion. Okay. You need to plot GHS where S equal to in the range of the J to J infinity in this portion only. That corresponding to, for example, the Nyquist plot, and we can see more example here. Okay, so from this point onwards, our exercise will be only on these portions. Okay, once we have that portion, basically here we make these portions. We only using this portion, we can tell right away whether this point -1, 0 is encircled or not. Okay, so we can take a break. We're gonna